So 6.5, exploring graphs of the reciprocal trig functions. So let's do a quick recall, okay? There are three trig ratios. They're called sine, cosine, and tangent, okay? Sine, cos, and tan for short. And when we write out SOHCAHTOA, we have sine theta equals O over H, right? O over H. Cos theta equals A over H, adjacent over hypotenuse. And then tan theta equals opposite over adjacent. Okay, and remember, we can only use the sine ratios, like if we're dealing with triangles, we can only use it with right triangles. Okay, however, we look at these when we are graphing like the sine and the cosine curves. Okay, so we also have three reciprocal trig ratios. So as a recall, reciprocal is like 1 over k. Okay, all it does is like you put 1 over your number and it flips it. Okay, so that's what a reciprocal does. Flips the number. Okay, so we have cosecant. So cosecant is CSC, and that is actually 1 over sine. So all you would do to the ratio is flip the hypotenuse and the opposite. Okay, so now it's hypotenuse over opposite. For secant, SEC. Okay, so 1 over cos theta. So again, you're taking the reciprocal, so you're flipping adjacent over hypotenuse to hypotenuse over adjacent, and then the cotangent is COT, cot sometimes, that's 1 over tan. So now we're flipping the opposite over adjacent to adjacent over opposite. Okay, so all of these ratios have just been flipped. That's what reciprocal trig ratios, that's what they are. So what we're going to do is we're going to investigate. So if you remember the 6.3 exploring graphs of the trig, the primary trig functions, if you remember this activity where I just took the sine one and then the solutions were posted on the website, what we're going to do is we're going to pull that out and we're going to complete the graphs of the reciprocal trig functions. Okay, so the first one we're going to do is we're going to sketch the graph of f of theta equals cosecant theta on 1 full rotation, so 0 to 2 pi. Okay, so looking at the points from 6.3, we are going to look at like 0, we have undefined. So for cosecant, there's going to be a vertical asymptote at 0. So it's going to be x equals 0. There, now we have the x coordinates here. So now we have pi by 6 and 2. So pi by 6. So here's the thing, pi by 2 is 90 degrees, right? Pi by 4 is right in the middle, it's 45 degrees. Pi by 3 is going to be 30 degrees, which makes sense, 30, 60, 90. And then over here is going to be pi by 6. So we're going to graph pi by 6, comma 2. So let's go 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. Okay, pi by 6 and 2. And now pi by 4 and root 2. So root 2 on your calculator is 1.4. Sorry, pi by 3 is on this side because it's 60 degrees. Okay, so pi by 6 and 2, pi by 4 and root 2, which is 1.4, and then pi by 3 and 2 over 3, or sorry, 2 over root 3. So if you put 2 over root 3 in your calculator, it's like 1.1. Okay, we have pi by 2 and 1. Okay, so this is going to look like this so far. Okay, remember there's that vertical asymptote here. 2 pi by 3 and 2 over root 3, which is that 1.1 again. Okay, 3 pi by 4 and root 2. So this is going to be 3 pi by 4. Okay, and then 5 pi by 6 and 2. And then at pi, we have undefined. So again, we have another vertical asymptote at pi. So that's x equals pi. So we're going to approach that like this. Okay, and then we keep going. So 7 pi by 6 and -2. So this is going to be 7 pi by 6 and -2. Okay, that's going to approach the vertical asymptote. 5 pi by 4 is going to be right in the middle, just like the 45 degrees is in the middle over here, 5 pi by 4. Okay, and then we have 4 pi by 3. And then we have -1. And then this is symmetric. Okay, and then at 2 pi we have undefined. Again, we have another vertical asymptote at 2 pi. So x equals 2 pi. Okay, if we take a look at these numbers in this grid, like every time we hit like this 0.1 or -1, say we hit 1, if we look on either side of 1, it's symmetric. Pi by 3 units away from the pi by 2 is going to be 2/√3. And then this is symmetric. Pi by 4 units away from pi by 2 is going to be √2. And then the next one's also symmetric. So pi by 6 units away is going to be 2. Okay, so there's no maximum because we approach infinity. So it just continuously increases. Okay, and then there's no minimum because we approach -infinity. So we continuously decrease as well. Okay, near those vertical asymptotes. Now, there's no amplitude because like there's no hump, right? Amplitude is only for sine and cosine. So we have to recognize that this is a completely different shape. And if we were to graph the sine or cosine, so cosecant theta equals 1/sine theta. If you were to graph the sine curve, it would look like this. Okay. Period. So just like the period in sine, the period for this is also going to be 2 pi. Okay. There is going to be an asymptote every single time that in the original, which is sine, every single time we have 0, so like an x-intercept in sine, there's going to be a vertical asymptote. And remember, that's because an x-intercept is 0. So if we're taking the reciprocal of 0, we're going to get some number over 0, right? 0 over some number. So we're going to get some number over 0, which is going to yield a vertical asymptote. Okay, the exact same thing that we went over when we were doing polynomials and rational functions. So there's going to be an asymptote at x equals 0, right? Because that's going to be our first asymptote. And then every period after. So no, not even every period. It's going to be every pi after. So at pi, there's another vertical asymptote. 2 pi, there's another vertical asymptote. 3 pi, another vertical asymptote, as well as going to the left. Because just like sine, the cosecant curve is periodic. So it's going to go to the right forever and to the left forever. So we can say we're going to start at the asymptotes at 0 and then plus minus pi n. Okay, the domain is going to be XER such that x cannot equal the asymptotes. So again, x cannot equal plus minus of pi n, and that's just n number of times. Okay. Now, the range is a little bit unique. Okay, we haven't really seen a range like this. So for this part of the curve that increases, we start at 1 and we increase to infinity. So the range is going to be 1 to infinity. Oh, but we include 1, so that's going to be square bracket 1 to infinity. And then on the part of the cosecant curve that opens down, we're going to start at -1 and we're going to go down to -infinity. So -infinity, because that's the smaller number, comma, -1, square brackets around the -1 because we include it. Okay, so now sketch the curve of f of theta equals secant theta for on like one rotation, which is 0 to 2 pi, okay? So we have the points for secant theta. Remember, this is the x, this is the y, or this is the theta, this is the f at theta, however you want to read that, okay? So we're going to graph 0, 1. Oh, and I'm going to go 1, 2, 3, 4, -1, -2, -3, -4. So 0, 1. Then pi by 6, which is here. In the middle is going to be pi by 4, and this is going to be pi by 3. So 2 over root 3. We've already seen these numbers, but if you put that back into your calculator, 2 over root 3 is 1.15. So anytime we see it in here, it's 1.15. Okay, 1.15 is a little bit higher. Okay, root 2. Okay, again, we already calculated this, but 1.4. Here we go, 1.4. Okay, so that's 1.4, a little bit higher. And then we have 2. Okay, and then at pi by 2, we have the vertical asymptote. Okay, so this is going to be x equals pi by 2. So this is going to be drawn approaching pi by 2, and it's going to approach infinity. Okay, now again, these are equidistant. Okay, so 60 to 90 is going to be the same as like 90 to 120. So pi by 3 to pi by 2 is going to be the same as pi by 2 to 2 pi by 3. So this is essentially 2 pi by 3. Okay, this 3 pi by 4 is going to be in the middle, 3 pi by 4. And then this 5 pi by 6 is going to be act as our like 60 degrees. So we have 2 pi by 3 and -2, negative root 2, which is -1.4. Okay, -2 over 3 is -1.1. And then at pi, we have -1. So we can connect those. And on this side, it's going to be symmetric. Okay, so then we have at this dash, we're going to have -1.1. At this dash, oh no, in the middle, we're going to have negative root 2, which is 1.4. And then here is -2. And this is going to approach the vertical asymptote here at 3 pi by 2. And I'm doing most of this, not even looking like referencing these points, but looking at the symmetry. Okay, 5 pi by 3, 2. 7 pi by 4, root 2. 11 pi by 6, 2 over root 3. And then we have 1. So just like cosecant, secant doesn't have a max or a min because it approaches infinity going up and it approaches -infinity going down. Okay, there's no amplitude. It's not sinusoidal. Okay, if we were to line this up with the cos curve, it would look like this. Okay, so period is 2 pi, just like the cos curve. We're essentially dealing with the cos curve, just the reciprocal. Asymptotes occur starting at pi by 2, plus minus every pi away, so pi n. Okay, asymptotes occur every single time there's an x-intercept in the original. Now, domain is going to be XER, such that x is not going to equal the vertical asymptotes, which we just pull from above here. and the range is going to be the same as cosecant. All right, number 3, sketch the curve of f theta equals cotangent theta on 0 to 2 pi. Okay, so sketch the curve of f of theta equals cotangent theta on 0 to 2 pi. Okay, so here are our points for cotangent theta. So 0 and undefined means that there's a vertical asymptote, x equals 0. Okay, pi by 6 and root 3. So on the side, we can be like, okay, well, what is root 3? Root 3 is like 1.7. Okay, so pi by 6 is going to be the first dash, and this is going to be 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, so 1.7. Okay, this is pi by 4, and then this is going to be pi by 3. So pi by 4 comma 1, pi by 3, and then 1 over root 3. So if we were to go 1 over root 3, I get almost 0.6, 0.6. Okay, so I'm going to draw this curve going like this so far. And then at pi by 2, we have 0. Okay, and then we're going to mimic what we just did on this side. So these two are going to be, instead of like 1 over root 3, it's going to be negative 1 over root 3. So we have negative 1.7. No, negative 0.6. Okay, then negative 1. And then negative root 3. Negative 1 should be here. Negative root 3 should be 1.7. Okay, and then we're going to have another vertical asymptote at pi. Okay, x equals pi. So we're going to go like this. Okay, now, if we can take a look here, these points are a replica of these points here. That means exactly how this part of the cotangent theta function looks, we're going to repeat that. So at 7 pi by 6, we're going to go root 3, which is 1.7. Okay, at 5 pi by 4, we're going to do 1. At 4 pi by 3, which is here, 4 pi by 3, we're going to graph 1 over root 3, which is 0.6, so 0.6. And then at 3 pi by 2, we're going to graph 0. Okay, so this is a complete repeat, which means like immediately you should be thinking, oh, well, since this is repeating already, the entire period is not 0 to 2 pi. It's going to be half of that, right? It's just going to be one stretch of this cotangent function. And then negative 0.6, okay, negative 1, negative 1.7, and then vertical asymptote again, x equals 2 pi. Okay, so then we're going to squiggle it down here, and this is the cotangent theta function. So max and min, there are none. We approach infinity and we approach negative infinity. So never, ever, ever will we ever reach a maximum or a minimum. We just continuously go. Okay, amplitude, none. This is not sinusoidal. It is not a sine graph or a cosine graph. The period's a little bit different. The period is just one stretch of this. So the period is 0 to pi. And there exists asymptotes starting at 0, and then plus minus, then we graph one at pi, then we graph one at 2 pi, 3 pi, 4 pi, and so on. So we're going to graph one every pi n. Okay, domain is going to be, well, I was going to say XER, it's technically theta ER, such that theta does not equal plus or minus the pi n, right? The exact same. We cannot equal an asymptote. Those are the only places where theta will not be defined. And the range comes from that max and min. Okay, so the range is negative infinity to infinity. All right, plus minus. This is plus minus pi n. It's not pi over n. So it's just like the asymptote here is going to be right here. Okay, so we, like our x value or theta value, okay, our independent value cannot equal the asymptotes. So conclusions. Which x values of the reciprocal function on the interval negative 2 pi to pi, or 2 pi, result in a vertical asymptote? Okay, and why does this happen? So I'm going to actually answer this generally. So every time there is an x-intercept, okay, i.e. means like kind of like a for example, or like I'm going to demonstrate x equals 0, there exists a vertical asymptote in the reciprocal, because 0 goes to, like 0 over some number goes to some number over 0, which is undefined. So if there is an x-intercept in the original, then there's a vertical asymptote in the reciprocal. Okay, and if there's a vertical asymptote in the original, then there's an x-intercept in the reciprocal. That's how that works, okay? What is the relationship between the positive and negative intervals of the primary trig functions and the positive and negative intervals of their reciprocal functions? So for the primary, if it's positive, then the reciprocal is also positive, right? So like positive means above the x-axis. Okay, and then for the reciprocal, or sorry, for primary, if the number is negative, well, when you flip it, the number is still negative, right? And then that would be like below the x-axis. Because all we're doing, so I'll just put like a little tidbit, because all we're doing is flipping the number, not the sign. So we're doing nothing with the sign. Positive is going to stay positive, negative is going to stay negative. Okay, C, where do the points of intersection occur for the primary trig functions and the reciprocal? Okay, so for sine theta and cosecant theta, they occur at max and mins. Okay, for cos theta and secant theta, again, they occur at max and mins. If you remember, we have something looking like this, okay, whether it be sine or cos, and so max, mins, okay, and so on. So those are going to be the points of intersection, okay? Now, for tan and cotangent, you can see here, pi by 4, 3 pi by 4, 5 pi by 4, 7 pi by 4. So for tan and cotangent, they intersect at pi by 4, plus or minus. And then what's the difference between pi by 4 and 3 pi by 4? Well, it's 2 pi by 4, which is 1 pi by 4, 1 pi by 2. So plus minus pi by 2 n number of times, because it's going to obviously continuously intersect. So overall key characteristics, the relationship between primary trig ratios and reciprocal functions. So the graph of the reciprocal has vertical asymptotes at each 0, which is like x-intercepts, of the corresponding primary trig ratio. The reciprocal function has the same positive and negative intervals as the corresponding primary trig function. Okay, we went over those. Intervals of increase on the primary trig function are intervals of decrease on the corresponding reciprocal function. And then vice versa, intervals of decrease on the primary are intervals of increase on the corresponding. Okay, and that's partly number sense. If you have a number, so as like a number gets bigger, so say you have like the number 2. Well, 1 over 2 is going to be the reciprocal. But then if you have the number 5, 1 over 5 is going to be the reciprocal. So as these numbers increase, the reciprocals are going to decrease. They're going to get smaller and smaller. And then vice versa. Okay. The ranges of the primary trig functions include 1 and -1. And that's where they intersect. If the primary trig function has a local minimum point, the corresponding reciprocal function has a local max at the same value. So this is the reciprocal, this would be the original. So min for original, no, that's max for original. This would be like a maximum, but it would be a minimum for the reciprocal. Okay, and vice versa. Okay, if the primary, so the original, has a local maximum, then the reciprocal is going to have a local minimum.